Hello, so in this chapter we're going to be looking at elastic strings and springs, and to start off with we're going to be looking at something called Hooke's law. Okay, now before we actually start, just want to remind that this whole chapter, so that includes this video, is going to be year 13 or the A level only. So if you're doing AS further math, you don't need to know this. Okay, no, don't need to bother with this. But if you're doing a full A level, then yes, here we this will be relevant. Okay, so as the chapter suggests, we're going to be looking at strings and springs. So strings and springs are going to be effectively the same thing. They're going to work in the same way, use the same formulas, so we can use them interchangeably, really. Okay. So what we're going to be looking at with strings and springs is when we compress, so when we condense or shorten them, or when we stretch them. Okay, so extend them. As you can see in this little picture here, that's very simply what we're going to be looking at. Okay, right. And so when we do compress or stretch it, that then produces a force in the string. Okay, and the idea is with this force, which for example is tension, which you might be very familiar with, the main idea with a string or spring is that strings or springs do not like being compressed or stretched. Okay, which means in terms of forces, so it produces a force to oppose any compression or stretching. Okay. Okay, so let's have a look at this then. So what I've done here is to really help visualize, because I think with this chapter it's very difficult to visualize sometimes. So I'm going to include various pictures throughout. What we're going to investigate then is very simply, in very simple terms, how the forces or the force in a string or spring works. Okay, so again, the main idea is the string doesn't like to be compressed or stretched, so it kind of opposes it. Okay, so let's have a look at this example first on the left. You can see that this finger on the right is stretching the spring forward, so the stretching is to the right there. Okay, so the spring doesn't like that, so what happens is there's a force inside the spring that acts the other way to the left. Okay, this is going to be a tension force. Okay, so there we are, so it acts the opposite way to the stretching. Okay, then we got this example. This is now compressing. Okay, so what's happening here is the finger on the top is now pressing down on this spring, so the compression is downwards like this. Again, this spring doesn't like that, so it's going to produce a force upwards in the spring to oppose it. Now, when it's compression, it's what we call a thrust force. Okay, so very simply, tension is the technical name when it's tension occurs during stretching. Okay, and thrust occurs during compression. Okay, so you might be very familiar with tension in a piece of string. Tension is specifically when something's being stretched. The thrust force is when it's being compressed. Okay, so hopefully with me here. Now the last example, we've got this tug of war situation. So actually this blue string is being stretched both ways. Okay, what I'm going to do is then split this in half like this. Okay, so we've got two halves of the string. Firstly, if we look at the right, okay, the guy on the right, again the string is being stretched to the right, which means on that half the tension is going to act there. Okay. Now, then on the left, again, the guy on the left is going to stretch the other way to the left, which means on that part of the string, it's then going to act to the right to oppose the stretching. So there we are. Okay. So hopefully that gives just the general gist of how these forces work. How the forces work in a string or spring. Okay, so it just acts the opposite way to what's happened to the stretching or compression. Okay, now we're gonna obviously we're gonna be looking at a formula then to actually work out this force. So it turns out that something called Hooke's law. It gives us a formula to work out the force, the tension or the thrust in the spring. Okay, so it goes like this. So the force in the string T is going to be equal to this lambda x over L. Now, what does that mean? Well, T obviously is my force, so that's going to be tension or thrust. Okay. And that's going to be newtons. Now this lambda here is what we call the modulus of elasticity. Now that is a number, and it basically just tells me how elastic a spring or string is. So how stretchy it is. Okay, so the higher the number, the more stretchy it is. Now x tells me the how much a spring has been stretched or compressed by. So it's the stretch. So it's what we call the extension. So the extension or compression, and that's a length in meters. Okay, and then L is what we call the natural length of the string. Okay, so that is basically sort of the length of the string normally. Okay, when no force acts on the string, so it's like the original length. Okay, and that's again going to be in meters. Okay, so for example, if we have a look at this top diagram, when it's static, so when there's no forces acting on a spring or string, this is what we call the natural length. Okay, that's all that means, right? Okay, and so this is the formula we're going to be using all throughout this whole chapter. T is lambda x over L. Okay, right. The last thing to note, actually two things. First of all, I'm going to jot down another formula, which might seem a bit obvious, but I think it might help if I write it down explicitly. And that is the total length of a string. The total length of a string or spring, that is going to be the normal length, so the natural length, so the original length, add on the extension. Okay, so when we stretch a string, we add on the extended part of the string to get the total length there. Okay, or instead, if we compress it, so we shorten the string, in that case the total length is going to be the normal length minus the compression. Okay, there we are. Okay, so you might perhaps that might seem a bit commonsensical, but it really might help to write that down. Okay, the last thing to note, you might be thinking, well, how come we didn't use this in normal maths? In normal maths, you hopefully you picked up on the fact you'll probably see this word thrown around a lot. Okay, inextensible. We cannot use Hooke's law when a string or spring is what we call inextensible. So what we're going to open up, what we're going to do in this chapter is now look at strings that are extensible. Okay, which allows us to use Hooke's law. So what I'm going to say is Hooke's law does not work with inextensible strings. Or springs. Okay, So there we are. But yeah, so that's really the main thing we're going to be looking at is T's lambda x over L. Okay, so we're going to look at some questions then. Here we're told one end of a light elastic string is attached to a fixed point. A force of 4 newtons is applied to the other end of the string as to stretch it. The natural length of the string is 3 meters and the modulus of elasticity is lambda newtons. From the total length of the string when lambda is 13. Okay, so firstly I'm just going to draw the situation. Again, in mechanics you do want to be drawing things out. What we're told is that one end of a string is at a fixed point. Now, what we can do there is, well, let's say we have some little surface. So let's say we have a ceiling and then the string is sort of hanging down. So let's say at this end of the string, that's attached to the ceiling. That's the fixed point, okay? So that's all that means, okay? So the string is attached to something like that. At one end. Now at the what we're told then at the other end, so at the bottom of the string here, we're told a force of 4 newtons is applied to the other end of the string. So what that's going to look like then, if we now, if I do another diagram, if we now put on this force, okay, so that's my normal string, but now I'm going to add on the force, okay. I'll do it in a different colour. So it's been stretched. So it's going to be stretching downwards like this. So there's going to be a force at the end that pulling it down, kind of tugging the string down. Okay. And that force is 4 newtons. Okay. So this red bit of the string is my extension. Okay. That's the extra part of the string when it's been stretched down, okay. And so the initial part in black, the initial part of the string is what is my natural length, okay. And again, this will be my natural length as well. So this diagram on the left is where nothing's happening to the string, okay. So hopefully you that makes sense. Right. Now, as for forces, well, again, as we discussed, the 4 newtons force is pulling it down. So this 4 newtons acts downwards. Now, as I said, the string doesn't like being stretched. So the force, the tension force is going to be opposite. So opposite downwards is going to go up the string. Okay, like this. So my tension acts up the string to oppose the downward stretching. Okay, so there we are. Now what we can do first is now actually resolve. We're going to resolve up and down the string. So firstly, my upward force is my tension T. Take away the downward force of 4. That's going to equal mass times acceleration. Now, there's no movement, so actually there's no acceleration. So mass times acceleration, so this is F equals ma. No acceleration means it equals 0. That means my tension force is 4. Okay. But they've not asked me to find the tension, they've asked me to find the total length of the string. So the total length of the string, if I do it in a different colour, is the whole length of the string after extension, right? So that's my total length. So I'm going to need to find the natural length and the extension. Right, but I'm told the natural length is 3 meters. So L for natural length is 3, which means this is going to be 3 meters. There we are. So I just need to find the extension, okay, the extra bit added. Right, the modulus of elasticity, lambda's 30. Okay. Right. Okay. So I'm going to go back to this. So T is 4. Now we're going to use Hooke's law. So T is lambda x over L. This is Hooke's law. So T is 4. By lambda, my modulus of elasticity is 30. Times x. So xn, remember x is my extension. So actually, this length in red is x. That's the extended part of the string. Okay, so I'm going to call that x. Okay, there we are. Then I'm going to divide by my natural length. My natural length again is 3. And so there, from this I can find x, my extension. So therefore 12 is 30x. So that means x, if I divide by 30, I get 0.4. Okay, but so then the total length of the string, so this is 0.4 meters, my total length is going to be 3.4. So 3 add 0.4, which is 3.4 meters. And there we are. Okay, so that's the core idea here. Right, let's have a look at another question. Right, so here I'm told an elastic string of one end fixed, particle of mass 4 is attached to the other end and hangs at rest. Find the extension of the string. Okay, obviously this diagram, I've added this for a reason, to help visualize the scenario. So what is the scenario? So what's happening here is we've got an elastic string. Again, one end is fixed, and then so there we are, one end's fixed. So let's say it's on a ceiling like this, it's going to hang down. Okay, what's going on here is we've got a particle, okay, and it's attached to the other end. Okay, so what's going to happen is if I draw this, when I draw the scenario, when I draw the string with this particle added on at the end, it's going to look like this. So it's going to stretch down because the ball, there's going to be some little ball thing, right, hanging at the end. Okay, hanging at the end of the string. And so you can imagine, and this is why I included the diagram, this is essentially what's going on if you're struggling to visualize it. We got some string and then the ball, a ball hanging at the end, stretching the string down. So hopefully you can visualize this. Okay, so again it's going to be an extension. I'm going to call that x. Okay, and then obviously the first part is going to be my natural length, but the natural length is 2. Okay, so hopefully that makes sense. Okay, that's the scenario here. Okay, so we've got some ball that's hanging at the end of the string to stretch it down. Now the particle has a mass of 4, so so the particle have a weight. Okay, the weight will act downwards, so there's a downwards force of 4g at the end there. So this weight force is what's pulling the string down. Okay, so it's stretching it downwards. Hopefully happy with that. Now, because the string is being stretched down, then the force in the string is going to act up. That's my tension acting up the string, okay, to oppose the downward stretch. Okay. So what I can do then is, again, I'm going to resolve up and down. So my upwards force is T. Take away the 4g acting down. That's going to equal 0 because, again, there's no acceleration because it's at rest. Okay. So that means T equals 4g. Well, actually, if g is 9.8, that means T is 39.2. And there we are. That's my tension force. Right. Okay. But we also know, because of Hooke's law, that T is lambda x over L. Okay, so tension is 39.2. Well, lambda, my modulus of elasticity is 29.4. My natural length is 2. Okay, so lambda 29.4 times my extension x over my natural length of 2. So my sort of original length, right? Okay, so now I can just solve for x. So 78.4 going to be 29.4x x. So therefore, x is going to be 8/3 meters. Okay, so there we are. So that's my extension. That's my extension of the string. So this extra bit in red, the extra part of the string, is 8/3, which again happens because the string is being extended or stretched down. So there we are. Okay. So again, hopefully you're happy with that, and hopefully you're happy with how the forces work. Okay. So now we've added some sort of ball at the end of the string, which forces it to stretch down, and so the tension force acts the other way to oppose it. Okay, and so there we are. Right. Okay, now we've got this question. So now we're going to be looking at compression, okay, which works in pretty much the same way. So here we're told a length of an elastic spring is reduced to 0.8 meters when a force of 20 newtons compresses it. Given that the modulus of elasticity is 25, find the natural length. Right, so what's going on here is, again, it's being compressed now, which again will kind of look like this diagram here, just to help visualize it. So again, let's just say normally, again, it's hanging down, my spring. And again, that's my natural length. Okay, but then it's being compressed. Okay, so what's going to happen is some just string is going to be the string is going to be compressed because there's going to be a force compressing it. So this force, if you're going to shrink, sort of condense or shrink the spring, there's going to be a force pushing into the spring like this. Okay, to compress it. Hopefully happy with that. This force is 20. Okay, so this is my compression force. Hopefully you can see it's acting upwards to push into the spring to condense it. Okay, and hopefully so there we are. Okay, right. So there we are. So now this is going to be my total length after the compression, right? This is how much spring I've got remaining after the compression. So this is my total length here. Okay, right. Now again, because now there's a force acting upwards, the spring doesn't like that. It's going to act the other way. So the force in the spring is going to act downwards to kind of push it out. So it's going to oppose the compression. And again, this is my force. This is going to be a thrust force now because it's compression. Anyway, so hopefully happy with that. So now, again, if I now resolve up and down, well, my upwards force is 20 newtons. Take away the tension, the thrust acting downwards. That's again going to equal 0 because there's no movement, okay? No acceleration, so that means T is 20. Okay. But of course we also know that T is lambda x over L. So if T is 20, that's going to equal lambda, which is 25, my modulus of elasticity, times x. Now x is now going to be my compression, so how much string has been compressed here, over my natural length L, and they want me to find the natural length L. Okay, so that means 20L. Actually, so 20L is 25x. Okay, so we need, so then that means L, if I divide by 20, 25 over 20 is 5 over 4x. Okay, that's about as much as we can do here. So we're good. So if we want to find the natural length L, well, then we're going to need to find x first, the compression. Right, so hopefully with me up to here. So what we were also told is the length of the spring is reduced to 0.8 meters. So that's telling me after compression, the spring is now just 0.8 meters, which is my total length, okay, here. So this is 0.8 meters, okay? Right. Well, of course, originally it was the natural length L, right? So if I do this, what I've done in purple is the part of the string originally that has been compressed, okay? This is my compression, okay? Which is X, okay? Now, hopefully then you can visualize that the natural or original length L is going to be the compression X added with 0.8 meters. Hopefully happy with that, right? Okay, so again, that's because the natural length, hopefully you can spot it's going to be adding these two lengths, they're the same. Okay, so there we are. Well, then we can rearrange to say that X is L minus 0.8. Well, actually now I can sub that into here. So that means L is 5 over 4 lots of L minus 0.8. Right? So now we can solve for L. So if I expand it, that's going to be 5 for L minus 1. Okay, so then that means that a quarter L is going to equal 1. So therefore L is going to be 4. So that is my natural length there. Okay, so we've got this question here. So here we're told an elastic spring of natural length 1.5 meters has one end attached to a fixed point and horizontal force of 6 newtons is applied to the other end and compresses the spring to a length of 1. Find the modulus of elasticity. Right, okay, so again, first we kind of need to visualize and draw what's going on. In this example, it's going to be a bit different to the other ones because now it's not going to be hanging down like this from the ceiling. That's not what's going on. Instead, it's going to be horizontal instead of vertical. So it's going to look like this instead, okay? Okay. The reason I know this is because it mentions a horizontal force, okay? So that's right and left rather than up and down. Now, what's going on here is there's a compression, okay? So what's going to happen here is, and again, I've added this picture here to help you visualize if you're a bit unsure of what exactly what it looks like. What's happening is, again, let's say the originally, right, this is my string. This is going to be my natural length, right? But now there's a force of 1 meter, there's a force of 6 newtons compressing it. So it's going to shorten this the string or the spring, right? And so you can see it's it's compressed and shortened the string. Okay, so now this is my total length. And there's my compression bit, which is missing. Okay. Right. So some things. Firstly, I know the natural length is 1.5. So actually, the original length is 1.5. I'm also told it compresses to 1 meter. So actually, the total length afterwards is 1 meter. That's how much the string is left, or the spring. Again, the same thing. Hopefully then you can spot the compression, how much has been compressed is going to be 0.5 meters. Okay. Because 1.5 take away 1 is 0.5. Okay. So I'll add that on. So compression was is 1.5 take away 1, which is 0.5. Okay, now in terms of forces, okay, so it's being compressed by this force of 6. So what's going to happen is there's going to be a force pressing into the spring. That force is 6, and it's going to then act to the left, right, to go into the spring, which means to oppose it, the force in the spring acts to the right. Okay, and that's going to be T. Technically, it's going to be a thrust force because we're dealing with compression here. Okay, so hopefully happy with that. So now, again, if I now resolve forwards and backwards, right and left, my T forces to the right, take away the 6 to the left, that's going to equal 0. There's no acceleration, no movement, so therefore T6, okay? But of course, we also know that T is lambda x over L, so T is 6. My modulus of elasticity is lambda, that's what it wants me to work out. X is going to be my compression now, not my extension. I worked that out, that's 0.5. Okay. And so L, my natural length, again, was 1.5. Okay. So actually I can find lambda quite easily now, right? So 6 times 1.5 is going to be 9 equals 0.5 lambda. So therefore lambda divided by 0.5, I get 18. So 18 there. And the units is newtons, by the way, for modulus of elasticity as well. But there we are.